Okay, so now that we have all the antiderivatives of trigonometric functions that we will need for the class, we can actually start getting into some examples. So the first one that we're going to deal with is the antiderivative of e to the x times tangent e to the x with respect to x. And of course here this seems a little bit more complicated. So we have tangent of e to the x, which is not too bad, but the thing that's complicating this is that it's e to the x and not just x, which means that, as usual, maybe the first reflex that we should have is to just replace our inside function with u to see if we can simplify this by using a substitution. So we would have u is equal to e to the x, which means that du would be equal to e to the x as well, dx. All right, and that means that I can now replace this e to the x dx by du, and now I have tangent of u. So I'll rewrite this integral as the integral of tangent of u times du. And I can now evaluate the antiderivative of this using the rules that we looked at last time. So that means we're going to go with rule number 7, which is the antiderivative of the tangent function. So the antiderivative of the tangent function is minus ln of absolute value of cosine of u plus c. And in this case, because u is actually e to the x, that means that our final result is going to be minus ln of cosine of e to the x. Right? And there's really no simplification that we can do here because cosine of e to the x cannot be simplified, and the ln is being applied to a cosine, which can also not be simplified. So that's it. That's our answer for the first question. For question B, I'm going to ask you to try to evaluate the integral of secant to the power of 7 of x times tangent of x. So at this point, please pause the video and try to solve this on your own based on the antiderivatives that we have already found in this class. All right, so in this type of problem, we have a function that is a little bit more complicated because we have secant to the power of 7 over here, right? So that means that, for example, if I had just the integral of tangent of x, then I could use rule number 7 in order to find the antiderivative of that. In the same way, if I had only the antiderivative, if I erased the secant to the power of 7 over here, I know that that would be the antiderivative of secant of x times tangent of x, and that would not be too bad. It would just be secant of x plus c. The problem here is that I want the antiderivative of secant to the power of 7, which means that power is complicating things quite a bit. Now, if I choose, so that means I'm probably going to have to do a substitution once again, or an integration by parts. You might have tried a couple of things, but for now I'm going to tell you this is going to be a substitution, okay? And the reason that I know that this is going to be solved using a substitution is that I know that I have a tangent of x over here, and I have secant of x to the power of 7. That means I have 7 factors of secant of x. So one way that I could rewrite this integral would be secant to the power of 6 of x times secant of x times tangent of x times dx. And if you want to, so if you look at this integral, you'll see now that what we've done is we've kind of just taken out an element over here that will allow us to replace du if I choose u to be secant of x, right? So I know that if I have a function secant of x and I differentiate it, I'm going to get secant of x times tangent of x. So this is where it becomes really important to know the functions, the trigonometric functions and their derivatives, because then you can foresee what function you're going to have to use as your substitution. So once again, here what I'm going to do is I'm going to choose u is equal to secant of x. Now, I already have a good idea that du is going to be secant x tangent x dx, but I have to find that independently, remember? So I'm going to evaluate just the derivative of secant of x, and I know that that's just secant x times tangent x, and of course dx. So now I can replace secant of x to the power of 6 by u to the power of 6, and my secant x tangent x dx is going to help me replace the u. If I rewrite my integral, that will give me the antiderivative of secant of x to the power of 6, which is u to the power of 6, times secant of x tangent of x dx, which is du. And I can now evaluate this in the way that I already know how to do that. So that means I'm going to get u to the power of 7 divided by 7 plus c. And if I back substitute, I will then get secant to the power of 7 of x divided by 7 plus the constant c. Okay, so this is the second example, just a simple substitution in which really the main challenge is to realize that you can select a given piece to be the du as long as you're able to remember that those are the derivatives that you're looking for. Okay, so once again, another problem would be C over here. And in C, I'm going to ask you to evaluate the integral of, so between 0 and pi over 4, so now we're talking about a definite integral of secant squared of x times square root of 1 plus tangent of x. Oops. All right, so again, pause and try to do it on your own and then come back to the video for the solution. All right, so here again, this is one of the problems in which you need to know what the derivatives of your trigonometric functions are, because if you do, you'll realize that the derivative of tangent of x is secant squared of x. And we've talked already about how it's usually a good idea to try to use a substitution in order to replace things that are inside a square root, because that way it makes the integral a lot easier to evaluate. So that means in this particular case, we would want to choose, even before we know how to do this problem, we would like to choose the inside of the square root to be the substitution. But knowing the fact that the derivative of tangent of x is secant squared of x already provides a hint that this will actually work, right? Because we already have the secant squared of x here. That means I'm going to choose u is equal to 1 plus tangent of x, which means that du will have to be the derivative of this function. And so derivative of 1 is 0, derivative of tangent is secant squared of x, and then this is dx, like this. All right, now, because I started with a definite integral, that means that I'm going to need to have a definite integral once I do my substitution as well. And that will require that I also change the bounds. So I'll have to change a to be 1 plus tangent of my original lower bound. So that's 1 plus tangent of 0. And then b will be replaced by 1 plus tangent of pi over 4. And so 1 plus tangent of 0 is equal to 0, because it's sine of 0, which is 0, over cosine of 0, which is 1. So that means this is going to be 1 plus sine of 0 divided by cosine of 0, which is equal to 0 over 1, which is equal to 0. And this is going to be equal to 1. And b is going to be 1 plus sine of pi over 4 divided by cosine of pi over 4. Both of these are square root of 2 over 2, which means that this whole thing gives me 1. And so I get that 1 plus tangent of pi over 4 is going to be equal to 2. Now I'm showing you how to do this without using a calculator, but of course in a test you would normally have a calculator, so you would be able to just plug it in. Just make sure that whatever calculator you use is set to radians. Okay, so now I have all the elements that I need in my integral. That means that I can now substitute it as the integral from a, which is 1 in my new variable, to b, which is 2 in my new variable. Then I can replace the 1 plus tangent of x by u, so that means I have square root of u. And then secant squared of x dx is going to be replaced by du. So I have du over here, which means that I'm actually integrating from 1 to 2, u to the power of 1/2 du, which is equal to u to the power of 3/2, so add 1, divide by the same power that you get, divided by 3/2, evaluated between 1 and 2. And at this point, I don't have to back substitute again. Remember, we already changed the bounds. In our integral, so that's why we found a and b in our new variable, which means we don't have to back substitute. We can replace these numbers into u right away. So I'll have 2/3, and then I'll replace 2 into u. So this is 2 to the power of 3/2 minus 1 to the power of 3/2, which tells me that this is 2/3 times 2 to the 2/3 minus 1. And that is my final answer. So it makes sense because I started with a definite integral, which means that in the end, my result should be just a number, right? So whenever we find an indefinite integral, that means we're going to be looking at a function as our final result, whereas for a definite integral, we'll have a number as our final result. All right, I'll do one last example. So that will be number d over here, and that will be the integral of cosecant squared of x divided by 1 minus cotangent of x with respect to x. And again, 2 minutes, try it on your own, and then come back for the solution. So once again, this is a case in which knowing your derivatives helps you figure out what you need to do, but also, you have a function at the denominator of this function. So you have 1 minus cotangent of x is at the denominator of a function, and so it would seem that the first thing we should try is to use that as a substitution, because hopefully that would make our denominator simpler and so our integral easier to evaluate. So if I choose u is equal to 1 minus cotangent of x, I'm going to have that du is equal to the derivative of this function, whatever that is. So that means I'm going to have minus the derivative of cotangent of x, which is minus cosecant squared of x dx. And that means that du is actually equal to just cosecant squared of x dx. And so I have that I can now replace cosecant squared of x dx by du. So this will be the integral and du over here. And 1 over, so this is like 1 times that, 1 over 1 minus cotangent of x is just going to be 1 over u. And so I have this, the integral of 1 over u du, which is just ln of absolute value of u plus c, and u in this case is just 1 minus cotangent of x. That means my final result is ln of 1 minus cotangent of x in absolute value plus my constant c.